Good morning, everybody. Everybody awake? Thank you, thank you. I think this is my 4th time in Minsk already, so I like the city. By the way, before I start, I always take a picture with you so I can prove to my colleagues that I've been working. Because they don't know where I am normally, and I can kind of show them. Smile, everybody. Yeah, you can also wave. Very good. Thank you. Okay, so let's make your day here fabulous. This talk is about trade-offs, and we'll see where we can take this. If you have any questions, just shout out at any time. So I work for Elastic, the company behind Elasticsearch, Logsearch, Kibana, Beats. Either you use us for full-text search or for logging or metrics and lots of other use cases. And I'm part of the infrastructure team and mostly spending my time now as a developer advocate, so I speak about the stuff that we do and try to show all the fun or good stuff that we have out there. So why did I get into this talk? I'm running 2 meetups back at home in Vienna. One of them is about databases in general, which is VienaDB. The other one is about more academic papers, where we read one academic paper each month and then discuss it. This is kind of a thing that papers we love, whatever city name. I'm not sure if you have one in Minsk, but this is kind of a global thing. They're called chapters, and there are chapters in a lot of cities all around the world. And I kind of had this idea that I could try to combine those things, a bit of theory behind like data structures, what is going on behind the scenes and why is stuff happening the way it is happening, and databases in general. So what is the perfect data store? That is a very common question that I have. Who thinks they know the perfect data store? Anybody? And if you think you have an answer, I would be interested in what the answer is. Sorry? Files, plain files. That might be a valid solution for some stuff. We can discuss that later on, why that might not always be the best case. But especially if you're a consultant, the phrase that you're probably saying most often is, it depends. Or at least that whenever somebody asks us something, the first answer is always, it depends. And depending on how much you have or how deep you want to go, you can then discuss further. But the first answer is always like, it depends. And this is kind of the idea of this talk, that you need to pick your trade-offs because there is no one perfect system. And even within one system, you can kind of tune it the right way to do stuff. So let's see what we can do. And I always say there is no magic, even though especially some vendors try to make you believe that there is magic and whatever you want to do, their system is just magically doing stuff for you. There is no such thing. So by the way, if you have any questions and you don't want to shout out, I'm generally using Slido, and I will just check at the end if anybody has typed in any questions. So Slido/my Twitter handle, and I think we should have time today at the end to do the questions, otherwise I would just tweet them out afterwards. But I think we'll have time today. So if you go to Slido/my Twitter handle, that is where you can just ask anything and I will answer it at the end. By the way, let's see if everybody is still awake or already awake. Where does my Twitter handle and where does this Xera thing come from? Did anybody guess that already? Let me give you a hint. It has something to do with my name. What could it be? And the sound bleed is kind of bad. Any ideas what the two could have to do with each other? If you take my last name and rotate the letters by 13, that is what you get. And 13 is kind of nice because if you rotate by 13 letters again, you're back at the original because, well, 26 letters in the alphabet. Okay, so that's where we got that. Okay, database trade-offs. This is probably the most well-known database trade-off, you know, the CAP theorem. Who knows the CAP theorem? Okay, that's still not everybody, so let's make that everybody. So the CAP theorem is based on this paper. I think the paper was published in 2002 and the idea was first presented in 2000 from Eric Brewer, even though he didn't write the paper. So it was by Gilbert and Lynch. They wrote the paper and he had this conjecture on the feasibility of consistent, available and partition-tolerant web services. It's not only about web services, it's about any distributed system in general. And basically, they say there are 3 attributes that you want to have, but you can have 2 at most. And those three attributes are consistent. In a distributed system, you want to have a total order. So it should appear as if you had a single instance of something and if you were talking to that one single instance, and not to a widely distributed system and you don't really know what the order is. So this is basically the order of events, and everything or every element in your distributed system should have the same order. That is kind of the consistency approach. The next one is availability. As soon or as long as a node is reachable, it should answer to your requests and respond. It doesn't define a timeout, which is sometimes critiqued about these systems because it doesn't say like how quickly a system has to respond, and that is kind of critical for any system. If it takes like 3 seconds to respond, nobody will be happy. But the CAP theorem basically just says it needs to respond to every request it gets. And the final element that you have is it needs to be partition tolerant. So even if you lose messages because the network is bad or because somewhere some switch drops them or whatever happens, it still should work as expected. And basically you can picture it like this. So you have the 3 attributes and you can at most have 2 of these attributes. If you design your system badly, you can only have 1 of these attributes or 0. Because of implementation errors. But at most you can have 2 of them. So you can see there is like no middle ground where you have all 3. And depending on what system you have, you will have different trade-offs of where you can go and what you can do. And generally the paper and how to prove it is very simple. It's not a lot of math, it's just pretty much by construction. So what it says, let's assume we have 3 nodes. So we have our 3 nodes. And then the network is partitioned. So you have on one side you have 2 nodes and on the other side you have 1 node. And the network is split basically between them. And so you have the network partition, and that's kind of a given for any distributed system. And then you need to decide, am I consistent or am I available? Because, for example, assume somebody is writing to these 2 nodes, and then they want to read the data back from this 1 node. And that 1 node then has to decide, am I consistent? Then I cannot answer anymore because I don't know what these other 2 nodes have received. Or am I available? Then I'm answering here, but I'm not consistent because these other 2 nodes might have received data that I cannot show. And that's just the entire idea of the CAP theorem. So it's very simple in itself. If you have kids or you want to explain to your parents or somebody else what did you do today or what did you learn, you can also explain it like Robinson Crusoe. So, you know, Robinson Crusoe, he was on his lonely island, he was basically alone. And the idea was that he is partitioned from the rest of the world, not the network, but the world in that case. And what he wants, and he knows kind of what he learned before he got to his island. And assume a ship comes by and asks him a current question. For example, it could be, who is the king of England? Because I think Robinson Crusoe was English, if I remember correctly. And then he has to decide, am I consistent? Because I don't know what happened in the rest of the world. I cannot answer. Then I'm not available. Or am I available and I answer, but then I'm probably not consistent anymore because somebody else, or there might be some news out there which I have not received. And then there's this thing called eventual consistency, where you have some lag and you always learn kind of like the current state, but with some lag. That would be the message in a bottle. So every now and then he gets a newspaper in a bottle and finds it on the beach, and that's how he learns what happened like a few months ago. But that's generally the CAP theorem idea that you have. There are systems that break that, but they are not very useful systems. So for example, if you write to def null, nothing will be there. And that is both consistent and available and partition tolerant, but that doesn't make it a very useful system. Yeah, while you can break it like this is not like a meaningful way. Coming to the next thing, that's why I called this talk fabulous. We have at Elastic, one of my colleagues, Mark, he came up with the fab theory. And it's pretty similar in the idea that you can have, or there are 3 attributes that you want, and you can only have 2 at most. And the fab theory basically says it's fast, accurate, and big is the fab theory. Fast means you can answer in near real time. So near real time might be like you might have a slight delay of 1 or 2 seconds or something like that, but it's something that people are willing to wait for. It's not like the batch processing where you go for a coffee and when you come back you will get the answer, and it might take 1, 2, 3, whatever minutes. So fast is kind of this near real time approach, what you often want from systems. The next one is accurate. which means you have exact results. Whatever the answer is that the system is giving you is the right answer. And it's not an approximation. And the final attribute that you want is big. Basically, you want to distribute your data. I know there's this whole discussion about what is big data and what is not big data, and everybody, when it was kind of the fancy term, everybody put big data on their product, even though nothing changed. But let's assume it's something that you need to parallelize. So you don't have it on a single node, but you have a cluster of multiple nodes working on your data. People sometimes have these Vs, like there are 3 Vs, like volume, veracity, and I'm missing one. Velocity, the speed, yeah. So volume is the amount of data, velocity is like how quickly it comes, and veracity might be how different it is. And some people have kind of overdone it and then said, like, nowadays, I think this came out this year or last year, now we're at 42 Vs. So basically every single word that starts with a V, they put into that big data topic and made it. And one of the Vs there, I think, is voodoo now. So at some point you have voodoo data. Which doesn't add a lot of value, but it's just one more V that you can slap on top of that. But yeah, generally, I don't like the term big data because it's widely overused, and yeah, let's do something more useful than saying, oh, big data again. So I guess fast is quite clear. You wait for it, and it's pretty much real time. You don't go for coffee. Big is you parallelize it over multiple machines. The accurate thing is kind of the one that is most unclear, and I want to show some examples what this accuracy or the trade-off around accuracy can be. So since I work for Elastic, I will use Elasticsearch as an example and use my queries there, but it applies to a lot of other database systems as well. So it's, even though the queries look different and the syntax is different, the approaches are pretty similar in other systems as well. Generally, the one concept that you need to know is that we have this concept of a shard, that you have one set of data and you can split it into multiple units, and this unit is called shard. So it's kind of one part of the data, and that can live on different servers, and the combination of these shards then gives you the final answer. Anybody knows where the term shard comes from? Where does it come from? Yes, exactly. Maybe more know this picture. Ultima Online, maybe some of you spent a lot of time there. So there was this evil wizard at some point, and there was this crystal where the essence of the world was stored. And at the end, the crystal was shattered. And then each shard of these crystals held one copy of the data. And that was, yeah, this is a concept that is quite some years old. But this is why this is always called shard, and a lot of systems talk about shards when they split up data. So I will run this in Docker because everybody has to use Docker, and every talk needs to include Docker nowadays. I think this should be the right Docker logo, by the way. That is much better. And we're the little Nemo fish down there. But yeah, that is the big Docker, and everybody uses the big Docker. So for my demo, if you want to reproduce it at home and download half the internet before, because, well, Docker containers, I'm using one Kibana instance to interact with it and one Elasticsearch instance. So it's not really distributed, by the way, simulate that distribution by having multiple shards on one single node. But it does everything that you would have in any distributed system. So nothing fancy going on here. We just have one node and store our data there. Okay, and I will start off with the term segregation. The term segregation is basically you have some terms and want to find out which is the most common term and how often does it appear. I will use as an example Star Wars, and I'm using the very first Star Wars movie, and I didn't count the terms myself, but somebody did that for me, and I'm just using the right amount of values. And this is how often specific words appeared in the original Star Wars movie. So Luke was the most common one, which appeared 64 times. That includes like the is, and, whatever. This is just like Star Wars specific terms or relevant terms for that. And then you can see R2 appears 31 times, and Alderaan 20 times, and so on. So these are all the words, and I'm storing each single word as one document. And what I want to then do is I want to count which is the most common word and how often does it appear. So I will split up my data into 5 shards. So one index with the data, I will split it up into 5 shards and store it there. And basically what I'm doing is I'm storing all the documents. I'm basically storing just one word. So you can see the word Luke, like the word, that is always the document. The first line is always kind of the meta information, so I store that in the index Star Wars in a specific type. I have some routing information, we'll get to that later on. And my document is just word and then Luke and R2 and send people and whatever. I'm just storing all these documents. And then, yeah, we can actually, by the way, I have all of this live here. So this is what this looks like. If you visualize it, these are all the terms I have in my set. And you can see Luke is the most common one, and then probably R2, and then Alderaan, Moby, or Obi-Wan. But we want to know how this got calculated in the background. So we want to run that query. So what we do here is, you can see this is what we have running. I have inserted the data already. And you can see if I search for Luke, here you get all your documents back. So this is the original document that I inserted. And that one appears 64 times. And then I have the other ones in the same number of occurrences. And now I want to run this simple aggregation. So this aggregation here doesn't do anything too fancy. Basically, I want to know the most common term, and I want to calculate it on this word. And I want the top one, the size here basically says I want one result, the top word, and I don't want the size 0. That one down here means I don't want the actual documents back, I just want the aggregation. I just want the count. So if I run that, how many results do you expect? Jumping back to this one, how many do you expect to get back? 64? Or do you expect something different? Yeah, the problem is, if I run that query, you can see here, it tells me it only got 56 Lukes, which is kind of unexpected. And we've done these. So that is the query we ran, that is the result we got, and then Luke would probably say something like that he cannot believe it. And it's impossible. And that is kind of like where we kind of made use of the fab theory, because it was fast, it was big data since we split it up into the 5 shards which we could have over multiple nodes, but it was not accurate, because we kind of traded a bit of accuracy for more performance. What did we do here? So I did mention earlier that I have this routing information here. And that routing information basically tells me on which shard I want to store one document. And I have skewed the data explicitly a bit, because normally this would not have happened like that. So initially, for the first 10 appearances, I inserted the first document in 0, then 1, then 2, up to 9. But after 9, I didn't start over with 0, 1, etc. But after 9, I put all of those documents into the 0 shard, or in the 0 routing information. So all the documents, the first 10 were evenly distributed, but the 54 others were going to the same routing key. And what happens behind the scenes, how does the routing key and the shard relate to each other? Basically, you hash that routing key, calculate it modulo the number of primary shards, and that is where the data will end up. So in my formula, that will mean the routing information, that was the number I've calculated. Modulo, what is the number of primary shards that I set? 5, which is also the default right now. So I hash my number, for example, I take 0, hash it. Anybody knows which hashing algorithm we use? It's called Murmur3. It's widely used, it's pretty fast, and it should very evenly distribute your data. So basically that we calculate Murmur3 of 0, have calculated modulo 5, and that gives me the shard information afterwards, where this will end up. Okay, and if you check out the shards, you can see the documents are kind of evenly distributed, because for the first document that I insert, I always kind of put the values higher than 10 always to the 0 shard. For the next term, I put all the values higher than 10 to the first shard, and the next one to the second. So overall, it looks kind of evenly distributed, but actually it's not. Because, for example, the Luke terms are all going to the 0 shard, which also got 70 documents and slightly more than the others. So how do we get these sub-results? This is how we calculate the sub-results for each single shard. Since this is a distributed system, we need to calculate that on each shard. So what each shard is giving me is getting the size, how many results do you want, times 1.45 plus 10. And that is the shard size. This is the top n results that every single shard is calculating. In my example, how many results will every single shard calculate? What was the size? 1 times 1.5 is, okay, plus 10. So how many results do you get back? 11 or 12? 11, because it's rounded down. So each single shard will give you its 11 best results. And the problem is, if your result is like, because you only have very few documents on that specific shard, you will not get all the results for that specific document, because Luke appeared only once in half of the shard, or in the other shards, the 0 shard had the majority, and the others just got 2 hits actually each. And so they might not be in the top 11 results each. And that is why this is skewed. But this makes it much more efficient, because each shard doesn't have to calculate all the terms, but only the top 11 ones and hand those over. Otherwise, it might be a very long list that every node needs to send over the network. So that is the optimization that we're doing there. Yeah, so per shard, we're getting 11 results. How many aggregates do we need to aggregate in total? 55, because every single shard is giving me the top 11 results, so 5 shards, so 55 results do we get in total, and that is what we need to aggregate. But you can imagine if you have more shards, or if your the results per shard are higher, the aggregation node needs to do more work. So this is the trade-off where we're headed. And actually you can see that, just to show you here, these two here already give you a hint of what is wrong with the result. So what it tells you is, I did not include 232 documents in that aggregation, because they were not in those top 55 results, basically, I calculated. Those were other ones. And then it also calculates an error upper bound. So basically what it does is, it knows for every single shard, I'm taking the top 11 results, and the occurrences of the 11th result is kind of like, that is the upper error bound. Because there could be a 12th result with the same number of occurrences, but we're not sending that, because we're only sending 12. And then you're calculating that error margin for every single shard, sum it up, and that is how you come to that 10. So that is the doc error count that you're calculating there. But you can fix this. Or instead of fixing, let's first try to figure out what is happening here. What you can do is you can show for one specific term how many errors you have. So if you run that query and add that parameter, it will add an upper bound of 9. So it will tell you for Luke, I calculated get the result 56 right now. But it could be 9 higher, so it could be 65 already as well, or any number in between. The actual result should be 64. So the upper bound is slightly too high, but it's getting very close. And you can kind of see where this is going. And the final thing what you can then do is you can then set that shard size explicitly. So the automatic value that you would calculate was 11. But if I say 20, it would give me the top 20 results from every single shard. And since we only had 18 terms that we're even searching for, 20 will definitely be correct. Because this will, yeah. How many results are we aggregating in total then? Yeah, almost, because we only have 18 terms. It's like 18 times 5. So it's only 90 in total. It doesn't change anything. If you have, if the shard size is higher than the tokens that you have, which is very uncommon because normally you have loads of tokens and you would always cut something off, then it's kind of 90 elements is, in our little demo here, is what we need to aggregate. And if you calculate that, it will tell us both the right result, and it will also tell me I don't have any error for this one, and I don't have any error overall. And the other documents that we counted, like there were 224 documents in other documents. So these 224 plus the 64, that should be the total occurrences of terms or the total number of documents in our system overall. So that is kind of this. We have ran through these queries. Okay, that is for aggregation. We have another thing where a very similar things happen around inverse document frequency. Inverse document frequency is part of the full text search, if anybody remembers that. So if I'm searching for Luke, and we've just stored the term Luke, and something very weird happens with that query. So if I have that query and I search for Luke, we have this score here. The score is basically the quality attribute. How well does this document satisfy my search query? And this is how we order documents by default. What is very weird is that the score here is different than this score. Oh no, these are the same, but here this score is different than this score, for example. And then if we scroll further down, see the scores are changing. Like this one is only 0.2, and it's the same document. Why is the same document having different scores? Why is the relevancy different here? That is one other optimization that we're doing in the background. And for that, you need to understand how full text search actually works. So yeah, here you can see the first two are I think the same. The third one is different, and the other ones are even more different. Yeah, that's kind of something you need to figure out, like what is going on behind the scenes, why is this happening? So how do we search, or how do we calculate the score or the relevancy? It's called term frequency and inverse document frequency, and the inverse document frequency is where we are doing an optimization again. TF-IDF is kind of this old name. Now we have changed the name or the implementation slightly to something called BM25, which is the new default, but it behaves generally the same. And BM25, by the way, stands for Best Match 25. It's the 25th implementation of a best match algorithm. And I'm not sure if we will get a BM30 or something like that in the future. That might be even better. But right now, it's the 25th iteration of the best match algorithm. So what we have is, for search, you have generally 3 parts that make up search and that score, which are the main factors for that. The first one is the term frequency. Basically, you take, if I search for Luke, and one document contains Luke 3 times and another document contains Luke once, the document that contains Luke 3 times is probably more relevant for my search for Luke than the other one. So basically, you take the number of occurrences, for example 3, and take the square root out of that. And the curves look something like this. So yeah, the curves between TF-IDF and BM25 changed slightly, but overall it's still the same approach. So the x-axis is how many times does my term appear, and the y-axis is how relevant does this make this. So you can see if you have 1 occurrence, it's pretty low, like 0 point something, but if you have 5 occurrences, it's almost 2 or 1.8 or something like that, the relevancy. And the more often it appears, the more relevant it is. However, with BM25, we figured out like if the term appears 10 or 20 times, doesn't make a major difference anymore. Whereas TF-IDF said that, yes, it's much more relevant still. But that's kind of like just flattening the curve a bit. The second part is we take the inverse document frequency, which basically means if a term is very common over all your documents, it's not that relevant. So basically very common terms are dampened in the relevancy. And basically what we say is, we say how many documents do we have totally, divided by that specific term, how often does it appear, take the log of that and calculate 1 plus. And the curve for that looks pretty much like that. So the x-axis is how often does one specific term appear over all the documents. So this could be how often does Luke appear over all the documents. And that would be then 64 times. So this, on that one, you could then go to on the x-axis to 64 and up to the y-axis on the relevancy, which means the more common the term is, like Luke, the less relevant it is, whereas very rare terms are more relevant. The final factor in that is, by the way, the field length norm, but that doesn't make any difference here because it's just like if some field is short, everything appearing in there is more relevant than in a very long field. For example, if you have a title which is short, if your search term appears there, it's more relevant than if you have the text body with thousands of other words, then it's not that relevant anymore. But since we only stored the term Luke in one document, that doesn't make any difference here. So what happens here and why is Luke so weirdly distributed? I mean, looking at the results, you can see the first Luke had 3.2 and the last Luke has 0.2. Like, that's a major difference. Like, something is off and like it's the same document. They should all be the same. What is happening behind the scenes? Why are we having that? So what we're doing is basically query then fetch. So if you imagine how a search query looks like, it works like this. So one is basically your client or your application sends a query to one random node. That is then the coordinating node. So in our example, the node 3 is the coordinating node. And the coordinating node figures out, okay, to search the data, I need to go to the shards 1 and 0. And it randomly picks any one of them. And it says, I'm going to the node 2 to fetch the 0 shard and to the node 1 to fetch the 1 shard. And it's basically sending a request to each one of them and says like, give me your best results for Luke. And by default, every node, so by default, the search result would give you the top 10 results. So what happens is every single shard has to return its own top 10 results. And it's basically sending back, okay, I have this score for Luke, and these are my top 10 Lukes, here you go. And that is the query phase. And then we have a second phase, the fetch phase, where we're basically saying that the coordinating node again tells the node like, okay, I figured out in total, these are the total 10 best Lukes. Now give me the actual documents. And all of those 10 could come from the same shard or they could come from different shards. So we're only getting the documents which are overall the best ones, but we're getting the score of the top one for each shard. So by default, with the 5 shards, we would get 5 times 10 the best Lukes, but fetch only the 10 best Lukes overall. So here we're fetching the 10 best Lukes, sending the 10 best Luke documents back, and then that coordinating node is sending the 10 best documents back to our application or client. So this is how a search works. So it's basically a two-phase approach, the query, then fetch. What we don't have is, if you remember back at the TF-IDF and the inverse document frequency, we need to know how commonly one term appears over all the documents. But there is no way to find out how commonly Luke appears over all the documents in this, because it doesn't take that into account. Because in the first phase, in the query phase, we're calculating the score, but we're not checking like the occurrences overall. For that, you could add another stage which is called DFS, query then fetch, and DFS stands for distributed frequency search. And basically we're adding a third step before the other two, where we actually calculate how commonly is Luke over all the documents. So it's kind of like sending, the cluster is calculating, okay, Luke appears 64 times overall, so this is the right number for my TF or for my IDF part to calculate that. It's basically just a parameter you add to the query, the DFS parameter, and if you run the query like that, if you run it for Luke, then you can see suddenly the score is 1.5 something for the first document, and it's still 1.5 something for the very last document, because the IDF part is now the same for all of them, and everything else was the same before already. So this is why the documents were not correctly scored before. Yeah, that was pretty easy. However, it's generally not necessary. Because then people always ask, like, how much performance does this cost? And this is my favorite comment whenever somebody asks something like this. Depending on how you do your setup or your demo, the results will vary greatly. For example, if somebody asks you, like, who is more intelligent, the house cat or the squid? If you have a demo scenario like this, the squid is more intelligent because you killed the cat. And you could totally tune any scenario to make one system faster than the other or skew the results. Generally, DFS will add some overhead because you have one more network round trip. And you need to fetch from the disk the distributions of the documents and then coordinate them together. So there will be some overhead. How much it is will depend on your network, how many shards you have and how many nodes are involved, how quick your disk is to actually get those statistics from disk, etc. So there is no percentage or specific value I could tell you how much it is. What I can tell you is that it's generally not necessary, because normally you have a lot of documents and then it will even out. And normally your documents will also be evenly distributed. For my little demo, I have explicitly skewed the data so that more data is in one shard and the data is very unevenly distributed then. This is normally not the case. Normally this is not a problem. And also our documentation says it really isn't required. So I don't want to give you the impression like, oh, the scores are always wrong and you should always use DFS, because that's not the case. It's just like something you should be aware of. Like if you either have very few documents in your entire system, or if you have some weird routing information where a lot of data goes to one shard and not the other, then it might be the case. For example, if you have like a news site and all your recent data goes to a specific node, so for example, you have a daily index with your news articles, and a new iPhone comes out, let's say the iPhone 9 or whatever comes next, then the data might be skewed because most of the reports will be on the today's shard about the iPhone 9, and then the data will be skewed versus the older data, or the other shards or indices will have different data. Then DFS might make sense, but it's generally not required. As long as your data is evenly distributed, you don't have that problem. And the other thing that you can always do is, you remember FAB stands for fast, accurate, big. Instead of taking out the accurate, you could always take out the big. So if you go to one shard, you don't have these problems anymore. And by the way, in 7, we will have a single shard as the default. Right now it's 5, but in 7 it will be 1. That was a change that we merged last week into the master branch. This is very new. And we've had like a 3-year discussion around that. Yeah. And this is Simon, by the way. This is one of the 4 co-founders of Elastic, and he's the tech lead of Elasticsearch. And he always says you should use a single shard until it blows up. And then you can calculate, okay, I can do this many queries or this much data in one shard. Overall, I have this many queries or this much data. So this is the number of shards I need. So take one shard, see when it blows up, and then you can get the actual amount or the right amount of shards. So if we change that, let's quickly do that. What I'm doing here is I'm saying I'm not writing to that index anymore. So I block the writes. And then I basically take the data from my Star Wars index and shrink it down into a new index called Star Wars single. And Star Wars single has a single shard. So we run this, and we have copied it. This copies over all the data as well. If I run my search query for query, and you see there is no DFS here. I just run the query, the original one that we had. And here you can see it gives you the right result right away without the DFS phase. Because basically we don't need to do any aggregations on the actual count, because it's one shard and it has the right number right away. And down to the very last one, all the results are correct. We can do the same thing with the aggregation. So what do you expect if I run the terms aggregation again? Will it give me the right result or not? Yes, because this one, you can see it gives me 64. Upper error bound is 0 documents were missed. Since we're getting how many results were we getting per shard? 11. It was 1, so the number of, it was the size, which is 1 times 1.5 plus 10, so 11. So each single shard gives me the top 11 results. Since I only have a single shard, it gives me 11 results, and that includes the top 1 result. So obviously this must be correct. By the way, you could set the shard size to a value only higher than the size. What some people think they could do is that they could do shard size. So let's say we wanted top 2 results, and we put, I only want to have 1 result. That doesn't make much sense, because giving me the top 1 result when I want 2 overall doesn't get me anywhere. So this will be implicit a shard size of 2 then. And if you run that, by the way, it still gives you the right result, because this one here will be ignored then in that case. Okay. Yeah. But that was kind of cheap to go to a single shard, because, well, we've got rid of big now. But we got accurate data instead. So it's kind of a trade-off. But you see, that is kind of the fab theory trade-off that we have. It's not an official paper. It's just like a theory or approach that we have, that if you have a lot of data and you want it fast, and then you probably need to trade the accuracy. Or you could trade a big of the speed, like DFS will take longer, but it will then give you a more exact result. So it's all about trade-offs in the data store, and you need to kind of know them to pick the right ones and tune them correctly. So to wrap up, it's pretty much all about the trade-offs in data stores. And what we've covered today was the CAP theorem, where it's mostly about correctness. How does your system behave, especially if something goes wrong? Does it lose data? Does it give you the correct result? Does it answer? Or the FAB theorem, or FAB theory, because it's only our theory, which is more about picking the right trade-offs and tuning the system to kind of behave the right way for your use case. Do you need quicker data, and do you want to spend less resources on that, or do you want more accurate data and tune for that? And those are kind of the levers where you can pull and where you can go. And that's it. Now we can jump to the questions. And by the way, I have some stickers up here. If anybody wants stickers afterwards, be quick. Questions? Any questions? Yes, please. Do we have a microphone, or do I have to? Otherwise, I will try to understand and repeat the question. Yeah? Wait, the microphone is coming. That's easier. Thank you.
Hello. So it's not clear that fast is not exact. I mean, it's can be relative. Fast, 1 minute is fast.
Yes.
Or half an hour is fast in some conditions. So can I get a feeling what means fast compared if I select fast and big but not accurate, or if I select fast and accurate, what would be the big? Just some numbers.
Right. So I mean, an exact number is hard to give you. But for example, if we go back to the DFS example here, this one gave you the exact result, but it was a bit slower than the other one. So we didn't get rid of the big because the data is still distributed, but it potentially takes a bit longer. And I don't know how much longer that might be. That might be 10%, or that might be 20% or something like that. So it's probably not, for that specific use case, huge. I mean, for real time, there are all these statistics of what even is real time. Like sometimes the perception is like it needs to be like 50 milliseconds, which is probably not for most database systems. My definition is pretty much like as long as I want to wait for that, which is like 1, 2, 3, whatever seconds, and not go for a coffee that is real time. But real time or near real time is kind of like very ill-defined and really depends on the use case. Which starts, by the way, if you have like a soccer match like tonight, is that even real time? Because that will be delayed by, I don't know, half a second or something like that until it reaches your TV screen. So I think real time is always like very much a perception that you have. For my use case, or for the way I want to use it here, it's pretty much, do you wait for it? Does it return soon, or do you go for a coffee until you get the result back? I hope that kind of answers the question. There is no answer like, oh, up to 1 second, that's fast, and 1.1 second is not fast anymore. It's kind of more of a spectrum where you can go. It's not like one specific value, but it's more like a tendency where you can go. Do we have a follow-up question? Wherever the microphone went.
So my question was more some real example. What the trade-off, how much fast I trade off compared to the accurate. In this, if you select some terabyte of data, not this example, I mean, to get some feeling, what is the trade-off, really?
Right, so generally the trade-off is if you're using anything in the Hadoop ecosystem, it's not fast anymore because this will take 20 seconds or minutes or whatever. Which is more like this data lake approach where you just throw in all your data and you search through it in a very slow approach. I would say like everything slower than 5 seconds, for example, I would not count as fast anymore. And that depends then on the technology.
Okay, I think that's answered.
Okay.
Thank you.
I think we had another question over there. Over there. Thank you.
Hey, great
Hi.
talk. Thanks for the
Thank you.
talk. So I'm not an Elasticsearch expert, but my questions might, you might consider it silly, but...
No silly
So,
questions.
Getting back to Simon and the single shard approach at initially, like when you need to go to the second shard or the third shard, do you need to do some extra work to, for example, to rebalance the shards so the data is spread like evenly, something like that?
So, to go to more than one shard, you will need to do something. So you have seen where is my example? This one here. Here I call a shrink to go from 5 shards to 1. You basically need to call the inverse operation, which will be underscore split, and take that data to split it into an index with multiple shards. This will be very fast because the data on disk will be hard linked. Split was only added in 6.2, but it's now possible to split that data up and then hard link it out. And then the master node, which keeps track of the cluster state. So there's always one master node in your cluster. And if I see my slide, so for example here, you can see there is one master node which has this green star, which is node 1 here. And that will basically know where each shard should be. And it will figure out after some time your cluster is not evenly balanced, and it will make sure that it will spread out the data. We also have this concept of the replica. So you see P is always a primary shard and R is a replica shard. The master node will also make sure that you never have the replica on the same node as the primary shard, because that doesn't make any sense. It would just double the disk space, but you don't gain any redundancy. Generally, you cannot make sure that the primary shards are all on different nodes, but the cluster state or the master node takes care of that and will make sure it more or less spreads it out evenly. What you could do, for example, if you have multiple racks and you want to make sure you have one copy per rack, then you could tag the nodes in the rack and say, this is one rack and the copy should be on another rack. Or if you have like AWS availability zones, you could say, this is my availability zone 0 and 1, and then you can tag the nodes accordingly, and then it would make sure that there is a backup copy or a replica in one of the other availability zones. So that is possible, but you don't have to explicitly say shard go there or move the shard around. That is what the master node or the cluster state is doing for you.
All right, thank you.
Sure, my pleasure. Any other questions? Yes, please.
Yeah, so still related to this single node, single shard approach.
Yeah.
For example, in this situation where we have 3 nodes, don't we lose something using a single shard, losing some network partitioning? So would we have more network partitioning issues? What I mean is that if you have 3 nodes and we have one single shard, the single shard will node, let's say, to the master, and a replica will go to a second node.
Yes.
But then the third node will do nothing, I guess.
Indeed. In that case, you will need to explicitly set the value that is a good match for your use case. Maybe let me step back. I think you're standing in the video, sorry.
Sorry.
So why are we changing to one single shard per node? That might be a very weird change. Because in the past we've seen a lot of problems were caused by oversharding, that people have had too many shards, and every shard has a specific overhead in terms of file handles and memory. And it also makes your queries a bit more complicated because you don't need to go to one single shard for the result, but you need to go to 5 and then combine those. So it adds some overhead. And a lot of people never thought about it and just went with the default and always had 5 shards. And then they have lots of indices, and then they have lots of indices times 5, and that often caused like a lot of overhead for the cluster. And we had people who like had thousands of shards per node. And that was not working very well. And that was for support, that was one of the main reasons why bad stuff happened. And we internally call this always the shard explosion, the shard explosion basically, that people just have too many shards. Because we have now the split API, you can split it up afterwards if you have more nodes. And I think That is not very final, or that is not final yet. But potentially in future versions, you will need to define the number of shards when you create the index. Potentially. And for example, if I remember correctly, beats, our collectors which collect data, have different default values for shards already. Because for most scenarios you don't need, especially if you have like a daily index pattern and you have you log data every single day, you don't need 5 shards for every single day. Because then if you have, let's say you keep 30 days of data in 30 indices times 5, you have 150 shards just for some log data. And that might be too much overhead. So that's why the default is changing. But you can totally override that. It's just something, that's why I included in the presentation. You should know what the default is and then to be able to set it accordingly. And I think we're out of time. Thanks everybody. Enjoy the rest of the conference.